Hello, we are Group 2 and will be presenting our project proposal and subsystem demonstration for the Mako XR Surgical Training in Virtual Reality project. Our team consists of Rithika Matthew, Heidi Nguyen, Ricky Liuan, Zara Williams, and Noel Darcy. We are all computer science majors in Engineering Design 1 for the spring 2025 semester. Our advisors are Hanji Zhuang and Dr. Sarah Taby. Our project is sponsored by the company Stryker.
Training for robotic-assisted orthopedic procedures, such as those involving the Mako surgical system, has traditionally demanded substantial resources, including specialized equipment, dedicated facilities, and intensive in-person instructions. These conventional methods are not only costly and logistically complex, but also limited in availability, restricting opportunities for comprehensive and frequent training. By simulating complex surgical workflows within an extended reality environment, training can become dramatically more efficient, scalable, and accessible, helping to overcome these long-standing barriers.
Now here is our proposed solution. 1. The primary goal of our project is to develop a comprehensive XR training platform that accurately simulates Mako robotic-assisted surgical workflows on the Oculus Quest 2. The platform will leverage patient-specific computed tomography, or commonly known as CT, data to enhance realism and effectiveness, and will also integrate machine learning-based feedback to assess trainee performance and provide real-time guidance. 2. Our subsystem demonstration involves obtaining high-quality 360 camera footage and displaying it on a VR headset, allowing the viewer to look around and observe details from every possible angle. We also employ Unity to add various functionalities to the video, such as interactable buttons and easy navigation between video files, all within the headset itself. The goal of this demo is to develop our skills at VR development with Unity, while also providing an example of how VR or XR displays will work with our main project. 3. A foundational feature of our XR training platform is to simulate Mako surgical workflows. The formal procedures of each surgery will be assembled and presented to the user for further training ease. Step-by-step surgical guidance will be integrated into the display through Unity. And 4. To fulfill its role as a functional training platform, the XR application will provide the user with detailed feedback consisting of metrics such as completion time, precision, and adherence to procedures. All of these metrics must be collected during the simulated surgery module, then compiled, analyzed, and presented to the user. Based off these user performance metrics, the system can also list out common errors and provide possible solutions, allowing the user to gain a deeper understanding of the surgical process.
Now I will be going over the system overview. The use case diagram shows interactions between two main actors, the surgeons and the instructors. Surgeons can launch the training application, upload CT scans and surgical workflows, view detailed 3D models and surgical tools, align the CT scan with the patient's physical body, and perform virtual surgeries, which includes two essential components: tracking hand and tool interaction with real-time precision, and receiving immediate feedback on technique and decision-making. This tracking enables performance evaluation, where instructors can generate comprehensive session reports that quantify the surgical performance, and they can replay the training sessions to review specific techniques or errors. This block diagram reveals the layered architecture of the four main subsystems, which we will go over in detail in the later slides. The system starts with two inputs, the patient CT scan and the Mako surgical workflow. These are processed into a 3D anatomical model and extracted surgical steps. The core app uses these to build the XR environment and surgical simulation engine. The user interface connects the surgeon to the simulation. Machine learning handles object and hand tracking and CT anatomy registration to ensure realistic interactions. Performance evaluation runs alongside analyzing surgeons' actions in real time, and the outputs are a guided training experience and performance analytics to track progress and improvement. The sequence diagram details the interactions between the four major subsystems and two human actors. The process begins when the surgeon launches the XR training application. Within approximately 10 seconds, the surgeon uploads the CT scan and surgical workflow data into the input processing subsystem, which then generates a detailed 3D anatomical model and workflow steps. The core application subsystem displays the immersive VR environment with surgical steps within 2 seconds, enabling the surgeon to interact with the virtual tools and UI elements. The system prompts the surgeon to align the CT scan with the patient's body, taking about 2 seconds to complete this critical registration step. Once alignment is completed, the training simulation begins. During simulation, the system enters a continuous loop that persists until the surgery is completed or terminated. Within this loop, the core application tracks hands and interactions in real time, sending this data to the machine learning subsystem, which returns tracking data and validation status. The core application requests performance evaluation, approximately 3 seconds, and receives feedback and error metrics from the machine learning subsystem. Based on this analysis, adaptive feedback is shown to the surgeon in real time. At session completion, performance data is sent to the output and analytics subsystem in approximately 1 second, which returns visualization and insights within 2 seconds for the surgeon to view. Simultaneously, the instructor receives a comprehensive session report with replay capabilities, completing the training cycle.
Now we will dive deeper into the subsystem design and implementation, with each subsystem being described by a different team member. The objective of this subsystem is to handle all incoming input from the user and either perform the necessary transformations on said input or direct user commands to the corresponding subsystems. Transformation of data makes up a large part of the subsystem's utility, with the main task being the processing of patient CT scans inputted by the user. By utilizing the Mako smart robotics technology, the subsystem is able to create three-dimensional surgical scans specific to each patient's anatomy. This subsystem is also responsible for compiling surgical information, such as tool usage patterns and surgical steps, and exporting that into a JSON or XML workflow file for later review. Lastly, the subsystem is additionally responsible for all prompts and output verification. This activity diagram on the left breaks down the input processing subsystem into two detailed workflows: CT to 3D model conversion and surgical workflow structuring. The CT to 3D model conversion involves prompting the user for a DICOM CT scan upload, segmenting the anatomy using a 3D slicer, then generating and exporting the anatomy as a 3D mesh model. Similarly, the surgical workflow starts by prompting the user to upload the necessary surgical process data, then compiles and exports the data as a workflow template. The main purpose of this diagram is to emphasize step-by-step operations, error handling, and output verification, showcasing how raw data is transformed into usable XR assets.
The objective of the core application subsystem is to orchestrate the life cycle of an XR-based surgical training session. It begins by initializing the Unity engine, setting up AR frameworks, and verifying Vision Pro capabilities to prepare the runtime environment. Once the engine is ready, the subsystem proceeds to load critical assets, including importing 3D patient models and surgical workflows, binding assets to Unity scene, and configuring physics and collision properties for realistic interaction. The system then transitions to a ready state, where it displays instructional panels, loads surgical tools into the XR space, and prepares the user interface for training. During the training phase, the subsystem actively tracks hand and tool interactions, stimulates anatomical responses using haptics and physics, delivers step-by-step guidance via the side UI, and logs user performance metrics in real time. It supports dynamic state transitions such as pausing and resuming the session without loss of progress. And upon completion of the procedure, the subsystem generates a final performance report, offers a replay option for review, and prepares the application for either starting a new session or exiting. This structured, state-driven approach ensures a seamless workflow and robust training outcomes within an immersive AXR environment.
Next, I'll walk through how the machine learning subsystem captures and analyzes user performance to make our training system smarter and more responsive. The machine learning subsystem plays a critical role as the intelligent backend of our surgical XR training platform. Its main goal is to enhance the training experience by analyzing motion data captured from the Oculus Quest 2 sensors. Using computer vision and time series analysis, our models interpret hand gestures, track tool positions, and evaluate movement patterns in real time. This real-time tracking is essential for determining whether trainees are using correct techniques, maintaining proper hand positioning, and following the correct sequence of actions throughout the procedure. After collecting this data, the system compares the trainee's performance against established expert benchmarks, focusing on metrics like movement precision, smoothness, timing, and tool alignment. It then generates an overall performance score and a personalized feedback report. These feedback reports highlight specific areas where the trainee excelled and where they needed improvement. One important feature is that the feedback is entirely objective and data-driven, removing the subjectivity that can often come with human evaluation. Trainees can reflect on their performance after each session, while instructors can use the performance trends to monitor progress over time and tailor coaching strategies. Beyond just evaluating skills, the ML subsystem also enables adaptive learning. This means the system can automatically adjust training difficulty or suggest specific exercises based on each user's individual needs, helping them master techniques more efficiently. Overall, the ML subsystem transforms our platform into a dynamic and personalized training tool, supporting both self-guided practice and instructor-led education.
The Output and Analytics subsystem is the final subsystem for our main project. This use case diagram represents the Output and Analytics subsystem, which showcases two actors. The first being the surgeon or trainee utilizing the simulation tool to learn and prepare through interactive virtual reality experiences. And then there's the instructor, which will be able to monitor the training activity in near real time and use this comprehensive data to provide the trainee with targeted feedback on performance. The surgeon or trainee engages directly with the virtual surgical environment while wearing a headset, manipulating instruments, and following predetermined workflows to improve skills in a safe simulated setting. Some data generated by the session that the instructor will be able to view includes movement and spatial data, like the accuracy and positioning from the user. This includes tracking hand motion precision relative to expert benchmarks, precision metrics of the tool in relation to the target anatomy, or measuring how accurately instruments are interacting with the virtual models, and times when the user hand positions leave the area of the patient's surgical zone. This measures boundary violations that could indicate procedural errors. These spatial metrics are critical for evaluating technical competence and identifying areas for improvement in surgical technique. The instructor will also be able to monitor if the trainee has completed the correct surgical sequence according to the input surgical workflow. This means verifying step completion and adherence to best practices. They will also be able to see the user's completion time for each step of the procedure, analyzing efficiency and identifying hesitation points. The system documents both overall procedure duration and time spent on individual surgical steps, allowing comparison against expert benchmarks and tracking improvement over multiple training sessions. This will occur in semi-real time as the trainee undergoes the simulation process using the headset, and the instructor is sent the performance evaluation data every approximately 3 seconds. For more information about that, refer to the core subsystem. The instructor interface represents both real-time monitoring views and summary reports, enabling comprehensive educational oversight. This data transmission creates a secure bridge between the trainee's immersive learning experience and the instructor's ability to provide evidence-based guidance, establishing a structured approach to surgical education.
Now we will be presenting the subsystem demo showcasing a virtual 360 application built in Unity, which we will be demonstrating live on Monday. The activity diagram illustrates the complete user flow of our 360 VR application. The process begins with the user putting on either an Apple Vision Pro or MetaQuest headset. Once equipped, the Unity XR app launches, initializing the XR environment and loading the default 360 video. The system then simultaneously executes 3 parallel processes, rendering the 360 video in the scene, enabling controller input for movement, and displaying UI elements with play, pause, and restart buttons. The user can move around using controllers while interacting with the interface. When the user selects a controller input, the system checks which UI button is clicked. Based on this input, the app either plays, pauses, or restarts the current video or navigates to a new file path. If a new file path is selected, the application loads the new video in the same scene. When the user chooses to exit, the application closes, terminating the session. Similarly, the component diagram reveals the underlying architecture that supports our 360 VR application. At the top level, the user interacts with either Apple Vision Pro or MetaQuest headset. The hardware to launch the application. The system uses several C# scripts to handle functionality, such as movement controller that tracks user position and movement, file loader, which manages video files, UI manager, which controls the user interface, button handler, which processes button inputs, and 360 video player, which renders immersive videos. For Apple Vision Pro, it uses Swift or Xcode, which enables platforms to integrate with the Unity Framework Bridge. The architecture keeps functionality modular and hardware flexible while ensuring a consistent VR experience. The architecture is designed with a clear separation, allowing for hardware flexibility between the different VR platforms while maintaining consistent functionality and user experience.
Thank you for considering our project proposal. Through this project, we hope to increase accessibility to the field of surgical robotics while simultaneously optimizing the cost efficiency of the training process for surgeons and medical assistants alike.